At Moffett Field, south of San Francisco, scientists have been researching into the details of crater formation by firing projectiles at high velocity down a barrel into a bucket of sand set on the floor of an evacuated chamber.
We can produce a hole in the ground. We can produce it with a very small object. A quarter-inch ball might produce a 20-inch diameter crater. It'll look conical in shape, but that won't be necessarily what a lunar impact crater will look like. Here's an example of a lunar crater, and to give you an idea of scale, the meteor crater, the Barringer crater in Arizona, would probably be about the size of this crater right here. This gives you an idea of the amount of energy that's involved when one of these events actually happens. It's a catastrophic process that is very difficult to imagine, and these experiments provide us only sort of a small glimpse of really what's going on.
In this shot, a thin layer of red tempera has been spread over the surface of the target so that the trajectories of particles in the surface layer can be followed in detail. The chamber must then be evacuated slowly. An electronic control system will fire the gun, having first switched on 3 high-speed cameras and their lights to record the impact in slow motion.
Well, I hope it works.
I hope so.
Any bets?
No.
If it works, I'll get you a donut.
Oh, if it doesn't, I gotta give you one.
That's right.
I'll get you one with the hole.
Every time you do one of these things, it's a little bit different. I don't know, it's sort of like opening a present. You never know what exactly is going to happen, especially when you take perhaps a day preparing a target, and then suddenly to have it work. I feel like and I'm constantly surprised. This is what's the beauty of doing experiments. You never know what's going to happen next.
Heavy.
Great. That's great. Okay, that did just what we expected. Here we can see where the red tempera that we had on the surface of the target has been covered by the lighter material that was below it. And you can see the decay, and eventually that of the thickness of that ejecta, and eventually it gives out about here, where it predominantly becomes red. And as you go farther out, you can see just primarily red clumps that have impacted. And these would have produced secondary craters had they been formed on the moon at a much larger scale.
And this is what the cameras recorded. An impact slowed down to 1/16 its normal speed. What do such pictures tell us?
One of the things that we can tell out of these experiments is that the process of cratering is a very orderly process. It's not this chaotic jumble that you might envision by looking at an old war movie or looking at the nuclear explosion. It looks very like a chaotic jumble, a cloud. Instead, in a vacuum condition, which we have for the moon, it forms a nice series of conical shape, inverted cones that marches outward. And as it marches outward, it doesn't change its form very much. And this marching outward is a result of the locus of ejecta material coming from the inside first and at the highest velocities and contributing to the top of the ejecta plume. The material that is down at the bottom of the plume is coming from deeper in the crater. And even after the crater is formed, this ejecta curtain simply keeps on marching outward in a beautiful, regimented way. And that's in contrast to what happens if we introduce the effect of an atmosphere. And here we find that the beautiful, symmetrical, even transparent ejecta curtain that marches outward is replaced by a much more complex curtain. We find that the material seems to be drawn in at the top and bulges out at the base. It's a very fundamental difference between impact in a vacuum and impact in an atmospheric environment. The net effect is that we can produce very strange-looking craters. They're strange in comparison to the moon, but they're dead ringers for many of the craters on Mars. And by varying the atmospheric pressure, increasing it, decreasing it, we can go through and look at almost all the various morphologies that we see. Now, here we've taken 2 photographs, cut them in 2, and then pieced them together. The right photograph is of Mars. The left photograph is of a crater that we produced in the laboratory. And we see that they're very similar. This is in a completely anhydrous environment without water. And we find that we form this ridge. And this ridge continues around and at about the same distance that we find for the Martian craters. We believe this ridge is produced by the dynamic motion of the atmosphere in response to the cratering event. It's that curled and that bowed ejecta curtain that we see. And behind that ejecta curtain, this is sweeping up material and then depositing it in a ridge. Now, that's just the atmospheric effect. Now, if we add water, then we add something else again. We add a lubricant. We add the possibility that once that material hits the ground, it'll flow. We add the possibility that the sizes of the ejecta may be decreased even more. So the laboratory gives us a feel of what may have happened for Mars.